Wait, people are actually checking every land ride against every water ride? That's O(n) times m thinking. You don't need all those comparisons. There's one tiny observation that cuts it to O of n plus m. Want full solution? Check this video.
We will solve the lead code problem, earliest finish time for land and water rides. This problem looks like a simple brute force problem, but there is a neat optimization hidden inside it. So we are given two categories of ride, land rides and water rides. Each ride has start time and duration, and we must take exactly one land ride and one water ride, and we can do them in either order. Our goal is to finish both rides as early as possible. Now, the most obvious solution here is brute force. For every land ride, we try every water ride. Check land, then water, or either check water, then land. And at the end, we compute the finishing time and keep the minimum answer. So if there are n land rides and m water rides, that give us the complexity of O of n times m. And that's exactly what many people will implement first. But can we do better? Yes. Let's look closely at the land and water scenario. Suppose I decided that my first ride must be a land ride. What information from the land rides actually matter? After finishing the first ride, I immediately move to the water ride. So again, let's take this as an example. We will take the scenario when we will do a land, then water. So the obvious solution is that for every land ride, let's say at index 0, we try every water ride. In this example, we have only one ride. Yeah, let's assume we have more than one. So for every land ride, we will try every water ride. And then we move to the next index in the land ride. And again, for this land ride, we will check every water ride. But our optimization is that if we decided to go, for example, first from land ride to water ride, after finishing the first ride, we immediately move to the water ride. And the only thing that affects the second step is the time when I finish the land ride. So among all of these land rides, I only care about the earliest finishing one. So for every land ride, its finish time is so if I'm processing the land ride, the finish time will equal to the land start time plus the duration. Let's make it of I and the duration. So we compute the minimum land finish, which is equal to the minimum value of the start plus duration among all of land rights. So the idea here that we will process all the land rights, searching for the right that will end first. Or in other words, the minimum land finish. Now, here is the important observation. Once we know the earliest possible land finish time, every other land right becomes irrelevant. Why? Because any land right that finishes later can never lead to a better final answer. So we will process all the land rights, searching for the minimum land finish. So let's write it. Process all land rights, then get the minimum land right. And uh, again, because any land right that finish later than this minimum land right can never lead to a better final answer. Because a later finish can only delay the start of the water right. So for land, then water right, we first compute the earliest land finish, then we try every possible water right. The water right here can have or can start at either its own opening time. So for the water right, it can either start at its own opening time, at its own opening time, or the time that we finish the land right. Why? In the first case, where it starts at its own time, that means that we have completed the land right at, let's say, time x, and the water right already started at either a time before x or at x. So the water time, start time, or the water right already started. Sorry, this is the second case. The time we finished the land right when the water right already started. While we start, the water right start at its own opening time when the water start time is greater than x. Because if we finished our land right at x and the water right didn't start yet, we have to wait until the water right started. So this is the two cases for the water right. Whatever it is, we in this case we have to take the maximum between these two times. So the finishing time will be the maximum of the earliest land time or land finish and the water start time plus water duration. We compute this value for every water right and keep the minimum. And that is the best answer for land to water rights. Then we have to repeat the exact same logic in reverse. We compute the earliest finished water right, then try every land right as the second right. That gives us the best answer for water then land rights. Finally, we take the minimum of these two results. So let's walk through the code. At first, we will define a helper function. Let's name it solve that take four vectors, the same as the main function. First, let's name the first start, and then have another vector, first duration, another vector, second start, and the last vector is second duration. So first, we find the earliest finish time in the first category. So I'll define a variable, let's call it earliest finish first. This is equal int max because we are searching for the minimum. Then we will iterate over the first start vector. So for int I equal 0 and I less than the first start dot size. We are defining this helper function because we need to do a land to water right and then a water to land right. So it's the same logic, but it is reversed. That's why I'm defining it as a helper function. So here I plus plus, and we need to get the earliest finish time. So this will be equal the minimum of the earliest finish time and the first start of I. Now we are processing the first write. Let's say in this example, it's going to be a land write. So we're processing all the land writes at each and every index I. So it's going to be first start plus first duration of I. And after that, I'll define a new variable. Let's call it answer, and this will equal in max as well. And then after we get the earliest finish time from the first write, we try every write in the second write. So again, for int I equals 0 and I is less than second start size and plus plus I. Our answer will be the minimum, the current answer, and the maximum between the earliest finish time and the second start of I. This is maps to the two cases we have talked about here, that we need to start either at the finish time of the land ride or at the water ride on opening time or starting time. So we'll define as the maximum between the earliest finish first and the second start, and this is plus the second duration of I. And finally, we return that. So return as. For the main function, it's just a simple call to our helper function. So we'll define land, then water, and we will call our solve function with same land time, land duration, water start time, and water duration. Then we will do the same. This will be water, then land, and finally we return the minimum between the two times. And that's all for this solution. So let's give it a run to make sure no syntax errors. So, oh yeah. Here we go. Let's submit it. And as you can see, this neat optimization leads to beating 100% of the solution. Again, this is a beautiful part in the complexity. Instead of checking every pair of ride, we scan each array only a few times. So still the time complexity is O of n plus m, but it's more optimized than the straightforward solution of checking for every land ride. We check every water ride, and again, we repeat the same steps for each water ride. We check every land ride. So if this explanation helped you understand the key observation behind the problem, don't forget to like the video and subscribe to the channel. Thanks for watching, and I'll see you in next video. Bye.